Hello, everyone. It's a great pleasure today and welcome together with me, Jacob Chakareski. He's currently an associate professor in the College of Computing at NGIT, where he also holds the Panasonic Chair of Sustainability and directs the lab for future AI-enabled wireless XR network systems and societal applications. He completed his PhD degree in EE and CS at Rice and Stanford University. He organized the first National Science Foundation Visioning Group workshop on future XR communications and network systems in 2018. He had several awards and distinct achievements lately, and it's a really great pleasure to have him today here. Well, without ado, I would like to welcome once again and thank Jacob. The stage is yours. Thank you.
Thank you, Zafer, for the kind introduction, and thank you to you and Neslihan for inviting me to give the presentation and for the help you provided to organize it. And without further ado, I would like to get started, and I hope everyone can hear me well. So my name is Jacob Chakareski, and the title of my presentation is Next Generation Wireless Systems at the Nexus of Machine Learning, Mobile XR, and UAV-IoT. And we are very grateful to our sponsors for supporting our investigations. As this is my first time giving a talk at Koç, I will start with a brief introduction about myself. As Zafer said, I'm an associate professor at NGIT, where I hold the Panasonic Chair of Sustainability. This chair basically provides some funding for me to pursue studies that aim to advance sustainability and environmental and energy conservation using the means of emerging technology that I explore. I have a bigger group that comprises around 8 students, several postdocs, and multiple developers. And we pursue a variety of externally funded projects. We still have multiple openings to fill in at all levels, and therefore to everyone in the audience that may be interested, I would strongly encourage you to contact me and reach out if you like the topics that I will cover in my presentation. We have a broad collaboration network spanning a variety of universities in the US as well as internationally, and a number of companies mostly located on the west coast of the United States. And the theme of the talk basically reflects a recent shift in paradigm of research of wireless networks, where now researchers have started increasingly look at other aspects of wireless network beyond just increasing the physical layer data rate that is enabled. And so these aspects that are becoming more prevalent now are exploring wireless networks or wireless network systems that are more robust to system components failures. They're more resilient to attacks. They're more integrated with key emerging applications, such as virtual and augmented reality, and integrate more closely quality of aspects related to such applications. And they're intelligent and able to self-coordinate their operation. And so within this theme, I will present 3 topics or 3 stories of research that we have explored recently. And the first one is on multi-connectivity and edge computing enabled mobile multi-user VR. The second one is on domain-aware fast reinforcement learning for IoT systems. And the third one is on real-time point cloud air streaming. And as an illustration of the interdisciplinary studies that we also pursue, I'll talk about an NIH project that we have on how we can integrate AI and VR to enable low vision rehab. And I will explain what does that mean, and I will then conclude and leave the floor open for questions and prospective collaboration if you are interested to discuss that. I will present like a few slides of why virtual and augmented reality are important. Many people expect that they will have a tremendous societal impact, advancing a variety of disciplines and fields such as disaster relief, remote monitoring, remote control of robots, telemedicine, telework, and a variety of other fields. And many have hailed the virtual augmented reality as the fourth disruptive technology wave after PC, web, and mobile. And so basically they allow us to virtually travel to remote spaces or bring virtual objects into our immediate environment, displayed both in each case on our wearable headsets. Now, unfortunately, so far the applications of this technology have been limited to offline settings, gaming, entertainment, low fidelity graphics, cabled operation, and high-end computing support. And the reason for that is that these applications are very demanding in terms of data they need as well as computation. And they also require very low latency in order to support seamless operation. And so this presents a broad mismatch with existing capabilities of network systems today. And our approach is to try to address these challenges with a holistic integration of emerging technologies as well as unconventional methods to bridge these performance gaps to enable the next generation of VR and AR applications that can make broad impact on our society. And as it is expected, and as you can probably imagine easily, the highest impact that these applications can have if they can be deployed without any cable attachment and with very high quality content, so that we have this lifelike suspension of ourselves in a remote environment, or lifelike impression of different objects and people being immersed into our immediate environment, so that we suspend our disbelief that we are at different locations. And thereby we can advance quality of life, the global economy, energy and environmental conservation, and also as in the present case, we can also fight the impact of or address the impacts of the COVID pandemic. Now, there are several technologies that we try to use to leverage to overcome some of these setbacks presented by existing network systems. And the first one is we integrate high-frequency wireless technologies called millimeter wave or free space optics that enable us to send data at much higher data rates and therefore much lower delays. Now, these technologies also, as everything in engineering, there is a trade-off. These technologies come with different characteristics than traditional wireless technologies, where the beams that these technologies use are very narrow, and so therefore they lead to having very fragile directed links that needs to be addressed in order for these technologies to be successfully leveraged. We also use edge computing or edge-based operation to basically bring the data and the computing as close as possible to the user, to leverage the head-mounted devices that are not able to provide the required computation by themselves. And therefore, we use effective representation of the data that needs to be sent to the user to enable something called viewport adaptation and ray distortion trade-off. And we do that through like scalable multi-layer 360-degree video tiling. And if you're not familiar, we'll explain that briefly on the next slides. What does it mean? So a brief introduction to how VR works. The setup basically comprises at present a very powerful GPU-equipped desktop computer, a gaming computer typically, where computer graphics 3D scene model resides, and the user is connected to the computer through HDMI cable typically, and in the direction of the computer, what we send, can you see my laser pointer?
Yes, Jacob, we can see it.
All right, very good. So in the direction of the computer, basically the user who participates in a virtual reality simulation sends the head orientation, which is basically captured by these three canonical rotation angles around the three axes shown here, centered on the VR headset worn by the user. And so these three navigation angles are also known as roll, yaw, and pitch. And once the computer has this head orientation, it will create the right view for the user on the headset within the simulation that evolves. Basically, the computer will render the right 3D viewpoint for the user based on the direction of viewing. Now, this is called 3 degrees of freedom, and it's governed by the 3 head navigation angles. And if the user is also able to move within, physically, you know, like within the simulation, then the virtual reality enables 6 degrees of freedom, meaning in addition to head orientation, you know, like you can also be at any location X, Y, Z within certain limited space. Okay. Now, another technology that we leverage is called a 360-degree video, and this is a new video format that is captured by an omnidirectional camera that captures light or light waves from every direction. And then this signal basically lives on a sphere centered around the camera. And so therefore, if the user is basically observing this content on a VR headset, it will have the feeling that the user is basically located where the camera was, where the content was captured, and he will have the feeling of 360-degree look around of the scene around the capturing sensor that is the camera. And this is similar to how we observe the scene around us when we are in a location. We can basically look around and see the scene around us with a 360-degree viewing angle. Okay. Now, to facilitate compression of this signal, because compression is needed to reduce the amount of data that needs to be sent or recorded, this omnidirectional video format is mapped to a 2D format, which is often looks like an equirectangle shown here. And then to also facilitate further compression, to further facilitate video compression, this wide panorama, this 2D panorama, is basically split into multiple sectors called tiles that are compressed independently. Now, when the user wants to see this content and is located somewhere else, you know, like this content is delivered over a network, and what the user sees at any point of time on his VR headset is a very small portion of that panorama, which is called a user viewport. Okay. Now, what we facilitate in our work, we have been able to formulate a very precise analytical ray distortion characterization of the trade-offs between the amount of data rate that is used to compress and transmit each of these small sectors called tiles, and the reconstruction quality or the distortion of that, the reconstruction error, which are inversely proportional in a one-to-one fashion of the tile. And similarly, we have been able to formulate what is the expected quality or distortion of the viewport that the user observes over time using this expression here, where the reconstruction error for each of the tiles is basically weighted by the probability that that tile, a given sector here, will appear in the user viewport over the amount of time over which we compute this expected viewport quality. And finally, what we also introduce in this context is that once we have such a video format, we can basically compress it in multiple layers of increasing quality, which is shown here to the right, where we have something called a base layer, which is this first blue, plane of tiles. And the base layer will basically provide a baseline quality to the user, and then every layer above the base layer is called an enhancement layer. Then it could be one or multiple such layers. And by adding more layers to the baseline, to the base layer, we can progressively increase quality. And the reasons why sometimes content is encoded in a scalable fashion is that then, we can adaptively send more or less layers depending on what the available network bandwidth is, and provide the maximum possible quality to the user at any point of time with one single representation of the data. Now, what we propose at the system level to address all the challenges challenges is illustrated here at a very high level. In the system that we pursue to enable lifelike 6 degrees of freedom, virtual and augmented reality to multiple users simultaneously, we have an edge server that helps the user in terms of computing. So the required computing is shared between the edge server and the headset. Okay, the user has a 6 degrees of freedom viewport adaptive scalable representation of the content, and I will explain that a little later. Now, instead of sending the data to the user or one single wireless thing, we send in parallel the content to the user over 2 different wireless technologies. One is traditional wireless technology that we use today that sends data at 2.5 or 5 gigahertz. And a baseline representation of the content to the user is sent over this technology to enable reliability and robustness. And that is because these traditional wireless technologies do not need to have a line of sight between the transmitter and receiver. And they're more reliably received and decoded. On the other hand, because they cannot provide the required data rate to really enable high quality immersion, we also leverage this high frequency wireless technologies, either millimeter wave or FSO, that transmits data at much higher frequencies of 60 gigahertz and above. And therefore we send an enhancement content layer in parallel over this dual high frequency link. And in order to deal with the fragility of such links, because they are very narrow and they are very sensitive to misalignment between the transmitter and the receiver, if this helps bring the idea forward, think of it like a very narrow laser, a beam of light that is used to send the data. If the recipient is not in the line of this laser, in the line of sight of this laser, the user will not be able to receive any data. And therefore, we need to steer the beam towards the user all the time, and this is integrated in our system. And moreover, because we have so much transmission capacity for this high frequency link, we can even send raw uncompressed data over it. And it may seem counterintuitive at first, because we need to send like orders of magnitude more data. However, this enables us to basically decompress and render the required content ahead of time at the edge server, and then send it as raw data. And this will avoid, doing the decoding and rendering on the headset, and that will save time. So in the end-to-end picture, we'll still be able to, improve the quality while meeting the strict latency requirements. Now, the user, what it returns to the edge server is basically the navigation actions, the head orientation, as well as spatial position. Now, the user headsets, as a last detail, they need to integrate the receivers that will be able to receive data through 2 wireless technology in parallel, and then this scalable and content layers will need to be integrated there. And we published a tutorial article in the IEEE Signal Processing magazine that describes this in very fine detail. Now, here's like a high-level illustration how this would look like in a system context in our lab, where we have like an indoor arena system, VR system, where we have infrared tracking base station that together with the VR headset will identify very accurately and very finely over time where user is based in terms of XYZ and where is the user is looking at in terms of head orientation. Okay. Now on top of on the ceiling of the arena, we have this next generation high frequency wireless transmitters that can either use free space optics, which is basically sending data using either visible light or sending data using different types of lasers, or they can be millimeter wave transmitters. Now, in addition to these next generation transmitters, we also have sub-6 gigahertz access points. You can think of this as traditional Wi-Fi, and they are both connected to an edge server where the 6 degrees of freedom VR content resides. We have also split the area of the arena into smaller sectors called cells, and we have placed one high frequency transmitter above each such cell. And then, as I said, the sub-6 gigahertz access point for every user sends a baseline 360-degree view representation of the content for that location and of the user. And then through the associated high-frequency link, we only send a viewport-specific enhancement so that the specific viewing direction of the user will really get a boost in terms of quality. And there'll be more details coming along to explain this. So you can think of the 6 degrees of content representation for the data. If you have like a remote scene that you want to monitor immersely, you can think of it as a collection of like an infinite number of 360-degree viewpoints for different locations in the scene. Okay, and so each one of them can be represented as one 360-degree video, or you can think of it that way. And then based on the spatial location of the user and the head orientation, that server will basically synthesize the right spatial 360-degree video for that location. And furthermore, there will be an adaptation to the viewport of the user given the yaw, pitch, and roll, and that will basically lead to selecting the right tiles and layers to be sent to the user. And the following picture illustrates that in more detail, where given a certain spatial viewpoint, the server will basically compress the content into two scalable layers, as I explained before, and the full panorama baseline content, meaning the whole this blue rectangle with all the tiles, will be sent to the user of a sub-6 gigahertz link to enable application reliability. And I will explain briefly what does it mean. And then over the high frequency wireless link, we only send part of the enhancement layer that is narrowly focused on where the user is actually looking at for that spatial location to enable high quality immersion. Then at the user, when the two content layers arrive, the viewport portion of the baseline content and the viewport portion of the enhancement content are integrated to enable high quality viewport reconstruction at the client. Now, the tile selection and the rate allocation for each content layer are made rigorous via analysis, as I will explain next. Now, why one may ask, why do we send the entire panorama for the baseline content layer? And that is because, as I said, this high frequency link will require active steering of the transmitter towards the user. And in some instances, there may be rapid head movements, which will cause a misalignment, and therefore this high frequency link may not be available all the time. And in that instance, the user will need to fall back to using the baseline content that is always reliably received through the sub-6 gigahertz. You can go with the Wi-Fi link in this context. Now, moreover, even if the high frequency link is on and the content is received, because again of rapid head movements, what is sent over the high frequency link as a viewport content may not actually correspond to what the user is looking at the moment. And this mismatch, will basically make or render the enhancement layer content useless for the user. And therefore, the user can not do anything about it unless there is like the baseline content layer that can be always used to synthesize the viewport, albeit at lower quality, but still that will basically continue make the application run smoothest. I may have said a lot, but there are also other aspects of the system, how to design the headsets to be equipped with receivers for both technologies, the traditional and the emerging wireless technology, but I will leave that aside in the interest of time. So within the system, we solve two optimization problems. One is how to assign users to next generation wireless transmitters during a VR session. And then once users are assigned to transmitters, how do we allocate the computational and transmission resources in the system? That means across the server and the devices. Now let's look at how we deal with the transmitter assignment and steering. On the beginning of the session, we assume that every user is assigned to a given sector or cell in the system, and it's assigned to the transmitter that is sitting on top, that is illustrated in this illustration to the left. Now, as a user moves around, the transmitter basically actively follows the user, and it is being directed towards the direction where the user is. Okay, and that is illustrated in this this middle illustration here. Now, it may happen that as users move around, two or multiple users may appear in the same spatial sector, and their transmission beams will follow them. Now, if there is an overlap between beams, that in communications people will say then there is an interference, meaning these beams are like basically interfering with each other. And in order to minimize this impact of interference, we dynamically reassign transmitters to users as they move around to maximize the signal-to-noise ratio of the next generation wireless signal that they receive, either optical or millimeter wave. And that is because signal-to-noise ratio is inversely proportional to the distance between a user and a transmitter. We can formulate that assignment for, like in a rigorous way using this optimization, where we seek for the assignment lowercase pi from the family of assignments capital case pi, that basically map users U to a transmitter T, such that we minimize the biggest or the longest distance between a user and transmitter. Basically, what does this mean is that we tend to assign users to the closest transmitter where the user is, to maximize the quality and therefore the data rate that the user receives through these high frequency wireless links. Now, checking for every possible combination between users and transmitters have the complexity, have a combinatorial complexity, and we show formally that this is an NP-complete problem. And therefore, we resort to a lower complexity graph theoretic based solution, where we first construct a weighted bipartite graph, where there are two sets of nodes in the graph. One is users and the other one is transmitters, and that is illustrated here at the bottom. And we basically construct the graph with all prospective assignments as edges between nodes in the top layer, which is transmitters, and nodes in the bottom layer, which is users. And we assign weights to these edges, where the weight assigned on an edge is basically a distance between the user and transmitter. And therefore, to spare you the many mathematical details, we can formulate this assignment as bottleneck matching on this graph, where we aim to minimize the maximum size edge weight and find the assignment that has the smallest maximum edge weight. In other words, this is called we pursue the maximum size, meaning the full vertex matching, whose largest edge weight is the smallest possible. Okay, that is described by this problem. Now, we have formulated a very efficient algorithmic solution using a decomposition of this graph, using a decomposition known as Dulmich-Mendelssohn decomposition. And the solution basically boils down to building this, finding this assignment incrementally, where we threshold all the weights in the graph using a threshold that is increasing in value, and we iteratively adapt our solution by adding more and more links or matchings between the nodes in the graph until we have like a maximum size matching. And we won a best paper award last year at the conference, which took place in fact in Istanbul, with a paper that provided this solution, among others. Now, once we have a matching between users and transmitters, we are interested in maximizing the delivered viewport quality or viewport fidelity across all users in the system, given various computational and communications constraints. And all the details in the matter included in this paper and the accompanying archive preprint that is posted online. And this overall optimization, we can show it decomposes to the optimization problem that is solved for every user, and that is shown here. Now, to spare, to save time and spare you the mathematical details, the objective shown here is basically the viewport quality that is delivered to user, captured by the reconstruction error of the user. If you want to maximize the viewport quality that is equivalent to minimizing the viewport distortion or reconstruction error, which is basically captured by the objective function here. And the variables that we control here is how much data rate we assign to every tile at the baseline and the enhancement layer sent over the two wireless technologies. Then we also have a choice, as I said, to send some tiles pre-rendered, decoded and pre-rendered, and that is captured by this discrete set MR. And finally, we also have allocations of decoding and rendering capabilities of the headset that we need to solve. Now, there are some constraints that we need to meet, and the first constraint here basically captures all the computing and transmission latencies that contribute to an end-to-end latency for the system for the baseline content layer that's sent. And similarly, the second constraint reflects the same end-to-end latency for the enhancement layer sent over the next generation wireless technology. And there are also some rate constraints that stem from the fact of how much data rate, how the data rate is, how the content is encoded, like what is the minimum encoding rate and what is the maximum encoding rate. And finally, this last constraint here reflects the rendering capabilities of the content, meaning what we render, what we associate as a rendering capability or processing capability from the headset to process the baseline content and the enhancement layer content. For some reason, we use W to refer to baseline content and X to refer to enhancement layer content. That should not exceed the rendering capability of the headset, and similarly for the decoding capability of the headset. Now, as I said, we can formulate, as I introduced a little earlier, using our analytical advances, we can precisely capture, what is the expected viewport distortion or the expected viewport quality, shown using this expression where, we leverage our, like analytical modeling to say that the expected viewport quality is the sum, is basically the probability of a tile appearing in the viewport multiplied by the expected distortion for the tile. And here we have two summations because, as I said, some tiles will be sent pre-rendered and reconstructed at the maximum high possible quality, and some tiles will be basically sent compressed, and they will be integrated, the baseline and the content layer of the tiles at the receiver, and they will be displayed on the headset device. Now, to make the long story short, the problem that I showed on the previous page is complicated because it has some integer as well as continuous variables. So this is a mixed integer program problem, and we are able through some analysis to reformulate to geometric programming, which is a technique for solving optimization problems, and we formulate a very effective iterative solution that quickly converges. Now, to show you some results, I'll briefly describe the setup that we have in our lab to evaluate this. We split a 6x4 area in our lab into 6 cells, as illustrated here, and we use the Steam VR software and the OpenTrack software to basically send the data from an edge server, which is illustrated here as our lab computer. The content that we use is called Virtual Museum. It's a very popular 6 degrees of freedom VR content. There can be up to 18 users in the arena, and the users are equipped with the HTC Vive headset. The OpenTrack software allows us to basically accurately track the location and the head and orientation of the user up to 250 samples per second. And in this right illustration, we show, for instance, some navigation patterns of the user over the duration of a session. Now, we mentioned that each spatial 360-degree viewpoint is represented as a compressed 360-degree video. In our case, they are compressed at a very high 12K spatial resolution and 120 frames per second to enable a very high immersion fidelity. And we measure the delivered viewport quality to every user. We also compare to 2 state-of-the-art reference systems. Li-Fi is basically a cellular visible light communication system that only uses visible light to send data. And Dash is a very popular standards-based approach streaming video content, and in this case, we use it to stream 360-degree video content that only relies on Wi-Fi. Now, if we compare, like what is the viewport quality that is delivered to 6 users in the arena, we can see that we have a considerable improvement in our system. These color bars represent the expected viewport quality of our method, and these other 6 bars to the right describe the quality delivered in the case of this state-of-the-art reference system called Li-Fi. And we can see that on average, we have maybe 5 to 7 dBs of improvement in terms of quality, and that improvement is consistent. Moreover, the numbers on top illustrate the standard deviation. What is the variation of the viewport quality over the duration of the session? And we experience around 3 times smaller viewport deviation in terms of quality compared to Li-Fi. Moreover, we have also plotted here the average quality enabled by the Dash system that is using only traditional wireless to send the data. And we can see that Dash basically provides a very low quality of 39 decibels, which for the size and resolution of the content, the temporal frame rate is very inadequate. Sorry. Now, in our system, we observe that our user can, so our system is able to push up to 1.02 gigabits per second data rate, whereas in the case of Li-Fi, this data rate is around 550 megabits per second. So we are able to also send maybe twice as much data per unit of time using our advances. Now I want to show this graph that basically illustrates what why some system decisions have made this system the way they have been made. Here we show the temporal evolution of viewport quality over time, where on the x-axis we show time steps, and they are separated by 4 milliseconds because that's how finely we can sample, where the user is and where the user is looking at. And on the y-axis we show the viewport quality over time. Now we can see that at some point we have a dip here, and that happens that either because at that point of time the high frequency link was dropped, either due to sender receiver misalignment, or due to the fact that like the user rapidly moved his head, and therefore the delivered content for the viewport on the enhancement layer did not match with where the user is actually looking at, and therefore it could not be used. Now we can see that in the case of our system, there is a drop, but the drop is not as significant as in the case of 2 other systems that we compare. And I forgot to mention, in addition to Li-Fi, in this graph, we also evaluate the performance of our system, however, without the facility of using a parallel traditional wireless technology link. Therefore, this basically means proposed with no Wi-Fi. And when there is no such backup link, to basically enable the application to continue receiving data, what the other 2 systems, proposed no Wi-Fi and Li-Fi, can do is basically freeze the content on the headset, waiting for the high frequency link to be again being directed to the user and to receive data over that link. Whereas in our case, that the drop is there is some drop because we are not receiving the enhancement layer, but because we continuously receive the baseline content layer, the user is still able to experience its application. And on average, as we can see, our approach, provides around 5 to 7 dB viewport quality gains over our own solution without Wi-Fi and over Li-Fi, as well as 3 times smaller viewport quality standard deviation. Moreover, and this is key, our approach doesn't experience any application downtime, whereas proposed no Wi-Fi and Li-Fi experience around 20% of the time application downtime, where they do not have any data to show, and therefore the user is basically not seeing anything on the headset. Now, I want to suggest that if there are any questions, we do that in the end. But now I'll switch to the second story in our talk. Here we made an observation that there is a range of emerging applications such as autonomous driving, mobile virtual augmented reality, remote control of robots, etc., that push the capabilities of IoT systems. However, in many of these applications, we find that the IoT sensors and the transmission equipment will need to operate in dynamic, unknown environments that are not known ahead of time, and the statistical characteristics of the data sources are unknown also ahead of time. And therefore, there is no a lot of prior data to work with to basically build some models ahead of time. And this is a perfect setting or this is a suitable setting for a self-learning operation where the IoT system will basically need to learn what is the most optimal way of operating without any prior assumptions. And so what we carry out here is a study that looks at real-time machine learning. And when I'm saying machine learning, I mean reinforcement learning in particular. And we also look at both algorithmic as well as hardware advances in this context. So let me introduce a little bit what reinforcement learning is for people that may not be familiar. The high-level concept of reinforcement learning is that we have an agent and we have a system that interact over time, and an agent at time t may take an action a sub t, as illustrated here, and the system may be in a state s sub t. Then in response to the action and the state being in a state s sub t, the agent may read or observe a reward r sub t or a cost value c sub t, and then the state may transition to another state s sub t plus 1, at which point of time the user may take another action a sub t plus 1, etc. Okay, and there's a very nice textbook by Sutton and Barth on this topic. Now the agent is interested in finding the optimal decision policy pi that comprises all the actions of the system that either maximizes the cumulative reward over time and minimizes the cumulative cost. And so this typically leads to emphasizing or reinforcing good actions and de-emphasizing bad actions. It's similar to how we use, as humans learn as we are being born and we start to grow, like we basically tend to not to repeat the actions that are penalizing, but tend to repeat actions that are good for us. Now, this is a discrete learning problem and typically comprises learning a huge table of a 2D table that is enumerated by the possible actions and states, and the entries on this table are the associated reward or cost values. Now, in the context of our system that we are looking at a 5G IoT device that may be sensing some information. Let's say, like this is a sensor that is capturing some video from a remote location and it's sending it to a VR headset for reconstruction. And this sensor will have two queues. One queue is basically for the information that is being captured, and this queue will comprise a number of packets. And the sensor may also have energy harvesting capabilities. Now we introduce this for completeness, but everything that I will present in the analysis will work even without energy harvesting. And so at every time instance t, the sensor will get a new set of new number of packets L sub t being pushed in its data queue, as well as a number of energy packets that may be harvested from the environment. And then the sensor will decide at that point of time to transmit a number of packets y sub t to a receiver or a wireless base stations sitting somewhere else over a channel that varies over time with quality h sub t. Now, in this context, what we are interested in achieving is minimizing the energy consumption of the sensor so that the sensor operates as long as possible. And that is shown by this expected value of this infinite horizon, cumulative cost, which is weighted by this factor gamma sub t. If you're not familiar, this factor is less than 1 and typically tends to place more emphasis and actions carried out in the near future compared to action far in the future, and that is why it is there. Now, we are also interested in, because we are talking about IoT latency sensitive applications. We also have a constraint that says the latency that packets experience sitting in the queue should, the expected latency should not be exceeding some threshold delta. Okay. Otherwise, if we're not concerned about latency, let me also mention that the optimal policy of how the sensor is operating, meaning how many packets we send per unit of time, should always be 0, because that will conserve energy the most. However, these packets need to be sent within a certain time limit, and therefore we have this constraint here. Now, this is a constrained Markov decision problem. It has a formulation of this nature, and one can show that using the Lagrange multiplier method, the optimal solution for the problem will have this structure, and this is sometimes called the Bellman optimality equation, where this function v, which is also known as the value function, it's the objective function of this problem, where we take the objective function and multiply by lambda this constraint that we want to meet, and so using Lagrange multiplier method, Bellman showed in the end of 60s that the optimal solution will have this structure where this is the present cost and the latency factor multiplied by this expected value of this value function for the state S prime where the system may transition to. And oftentimes this this function within or after this minimization minimization expression here is called the optimal action value function, which basically describes what is the cost that the system, what is the optimal cost that the system can achieve if it takes a value, if the state is in a state, if the system is in a state S and it does a value of an action of Y is taken. Okay. Now, if these cost factors depend on the state on the system, the action taken, and these transition probabilities of the system are known ahead of time, we can compute the optimal value function, the optimal action value function, the optimal policy using dynamic programming. However, in many of these settings, the environment in which the sensor will operate is not known ahead of time, and the statistics of the data sources that are being captured are also not known ahead of time, and therefore they need to be learned using reinforcement learning that learns these models and makes decisions simultaneously. So there are two approaches that people have studied here in this context, and one is a model-free approach where we learn the value function of directly the policy without learning any model. Okay, and the most popular approach in this category is called Q-learning, which we may have heard of. There are other like actor critic, policy gradient, SARS, etc. Now there are also model-based approaches where first, a model is learned for the cost function and for the transition probabilities, and then you can use dynamic programming, for instance, and the Bellman equation to solve for the optimal value function, the policy. And some approaches in this context are approximated real-time dynamic programming and Dyna. However, both approaches are purely data-driven. They do not make any assumptions about the system ahead of time. And the model-free approaches are characterized with low complexity. However, and they're suitable for deployment on an IoT device, but they experience very slow convergence because it takes many iterations of learning to, identify the optimal policy. On the other hand, the model-based approaches are very fast in convergence, but they're very complex because, they're trying to learn models about the cost and the transition probabilities before they start learning the policy. So our objective is to get the best of both worlds, where we can be somewhere close to a model-free with low complexity, but we can learn this policy fast because in many of these emerging applications, learning policy as quickly as possible, it is essential for enabling good performance for the application. So let's go back to how the optimal solution should look like, and establish how, for instance, state-of-the-art Q-learning approach would operate in this context. So at the time point A, when we take an action A, at the time point T, when we take an action A, the agent will observe what is the cost that is induced by this action and what is the latency that, how long will packets need to wait in the queue before they're sent, for instance. And then the system will transition from state S to S prime. Now, we will have a running estimate for the value function at that iteration N, which we can update using this expression here, where, it's a basically weighted combination between the estimate of the value function for that state S multiplied by something called beta, plus 1 minus beta times the sample estimate for this function S, where the sample estimate is basically the current cost plus lambda times the current latency plus what is the value, the estimate for the value function for the state to which the system will transition. Okay, and typically this factor beta or 1 minus beta is called the learning rate. So basically we are learning the value function on the fly as we are taking actions and making observations. Now, to give you a high-level illustration of our advances in this context, before I actually explain them, in traditional RF, many methods have been proposed, and they're very general because they're data-driven. They do not integrate any basic knowledge about the system that within which they are operating, and so they are characterized by inefficient computing, memory, and convergence rate trade-offs. Now we integrate a concept called post-decision state learning, where basically we take advantage of some simple system models to accelerate the learning considerably. Now, the negative impact of that is that the computing complexity will increase. Then with some further analysis, we show that some state variables are statistically independent, and they're also statistically independent from the unknown dynamics of the system. And that allows for further learning acceleration. But again, every time we accelerate learning, there is a complexity increase in terms of computation that we need to carry out. And finally, through some analysis of the value function, we are able to show that the value function in our context has some structure that we can leverage to basically approximate it very closely in order for us to maintain fast learning and low complexity at the same time. And moreover, we are able to precisely characterize the approximation error versus computing and memory trade-offs in this context. And we have published a tutorial article on this in the IEEE Communications magazine last year. Now, what is a post-decision state that we introduced? So the post-decision state paradigm basically says we can introduce an intermediate state between the current state of the system, S sub t, and the next state of the system, S sub t plus 1, where the system transitioned to. And this intermediate state, S tilde at time t, basically captures what is the system state after an action takes place, but prior to the unknown dynamics. So to relate it to the example that we studied, let's say our system is characterized by how many packets are in the queue and what is the channel state. Okay. Now, when we take an action y sub t, we will empty some packets from the queue. So our state S tilde t is characterized by a state X tilde t and H tilde t, where X tilde t is basically how many packets were in the queue minus how many packets were sent at that time instant. Okay, and H tilde t is equal to H sub t. Okay, and then the unknown dynamics of the system takes place, where an unknown number, a random number of packets will arrive, well, because the sensor again captures some information, maybe captured another video frame, and the channel transition to another state. Now we can show that we can reformulate, like the value function for the regular states to post-decision states, and there is a one-to-one mapping with them. And then we need to basically solve for the optimal post-decision state value function V tilde. Okay, and this is the mapping between the original value function and the optimal post-decision state value function. So basically, this one may say at first look that, okay, now we need to learn, the post-decision state value function and optimal policy pi, and we have basically moved the problem to another paradigm. However, what is critical to note here that one update of the value function for a post-decision state S sub tilde will lead to updates of all state S sub t, where this linear requirement, where this linear condition is met. And this comes from the nature of this, how this post-decision state is defined. So basically, this will lead to faster learning convergence. Now, there is still limit on conversion rates here because we are doing an update of the value function for one post-decision state at a time. However, through some further analysis, we can show that the packet arrivals L sub t and the channel state H sub t are independent of the post-decision state Q backlog X tilde t. Okay, so that means with one observation of one realization of LT and HT, where this post-decision state S sub t, we will able to update all post-decision state S sub tilde that are defined by X tilde, meaning for any state X tilde and HT tilde. Okay, so this basically means that we can update the value function for a state S sub t tilde without actually visiting that state, without actually making an observation that will take us to that state. So updating the value function for most states will lead to complexity increases. But let me first show you what are the qualitative learning advances that we introduce in this context. Going back to our Q-learning baseline model, if we, for simplicity, we show in a 2D plane, the mapping between actions, meaning throughput, how many packets we decide to send, and the state of the system represented as how many packets are in the buffer, with one action Y and observation of state X, Q-learning would basically update the value function only for this white rectangle. Now, because we have introduced this basic system model for post-decision states, which says post-decision state X tilde is X minus Y, with one post-decision state update, we're able to update, in fact, a diagonal of values X and Y in the original space. Okay. Moreover, with our further virtual experience advances, for every white rectangle in one of the rows here, we'll be able to update the remaining values there without actually visiting those states, as I said. So technically, it means we can update the values for all entries in this 2D table. And to show the qualitative advantage, before I explain how we deal with the complexity increase, let me show how our system performs compared to Q-learning, where we examine two quantities. One is, the buffer delay, and the second one is the power consumption. And on the x-axis, we show time slots, meaning progression over time as our algorithms learn. So we can see that our approach that combines post-decision state learning and virtual experience learning meets the required latency constraint of 5 packets in the queue, not more than that, very quickly within 300 steps, and near optimal power, is achieved within 3,000 steps. And this is basically how much power we consume to send the data, as I explained earlier. Now, in the case of PDS learning, it means the delay constraint at somewhat lower rate because it doesn't leverage virtual experience learning on top, but it's still much better than Q-learning. And we see that with PDS learning only, we consume around 20% more power compared to the optimal solution that combines both PDS and virtual experience learning. And finally, Q-learning basically performs the worst of 3 approaches as expected. We can see that it could never meet the desired latency constraints of only 5 packets in the queue of delay. And the power consumption also of Q-learning is much higher. And this comes from the fact that I said virtual experience learning, Q-learning learns at a much slower rate. And finally, we were able to show that the value function has some structural properties, and the value function basically quantifies the long-term performance of an optimal policy pi. And what we're able to formally show that this value function V star in our context is monotonic, and it shows increasing differences with respect to buffer and battery state X and E. And it's also monotonic and submodular with respect to the pair of buffer states and battery states. Okay. And we have formulated an algorithmic approach where we can basically closely approximate this value function while enabling fast convergence for our learning approach, so that we can basically compute the policy pi star very quickly online at lower complexity. And the way we deal with this is illustrated here. We approximate the value function using a low rank model. In this case, this is a piecewise planar approximation, where we basically sample the value function at a set of points that we select using our optimization, and then we approximated this piecewise planar, smaller regions at every other point beyond the points at which we sample. So our optimization basically says we can update the value function only on a small subset of points, and we can approximate it closely everywhere else. And we are able to show that, because of the properties of our learning expression, we converge with probability 1 to the optimal value function, the optimal policy, as we continue to learn. And then we are able to also guarantee that, the approximation is within a very fine factor delta L for each of the regions where we approximate the value function. I will spare you the details. We have a transaction signal processing paper that describes all the math behind it. Now, what we realized that if you want to deploy this on a hardware device, on an IoT device, it involves some computationally expensive operations of multiplications, and also it requires knowing this full distribution P sub k. And therefore, if we try to implement this like in a straightforward fashion, it may not be able to run on an IoT device which has limited computing and memory capabilities. However, through some observations, we have been able to see that there are some inefficiencies in the way this implementation would be carried out by default. So, for instance, knowing this distribution requires, computing it every time we need to do a learning update, but that can be factorized, and some factors can be reused without computing it over and over. There are some ways of how the states are mapped to the initial memory on the device, etc. And so, we are basically carried out a supplementary study with a colleague who has experience in hardware acceleration for machine learning, how to address these challenges to, enable real-time deployment on IoT devices. And to spare you the details, we have optimized the way some of these values are computed using lookup tables, the way how these states are represented on the device using a smaller number of bits. We have used parallel tree structures to compute this transition probability distribution, etc. And so this is our schematic of the how this is implemented in hardware. But what I want to truly show is what are the further benefits of the hardware accelerator. We have implemented our approach on a hardware on IoT device, and we have implemented Q-learning on our device, on the same device. And the graph here basically shows the cumulative average cost over time for our approach and PDS learning, and for PDS learning and Q learning. And we can see that our approach, converges much faster and exhibits lower average cost, whereas Q learning, takes much longer, to start converging. And so, relative to Q learning, we observe a 12 times faster convergence, 83 per second reduction in delay, and 59% reduction in power consumption. And we observe also 49 times acceleration of a software implementation, and 3 times faster and 85% lower power consumption of a baseline hardware implementation, or we will not be using our tricks. Now, if we have a little bit more time, I will try to explain another approach that we also leverage in this context, and we have published this in the IEEE journal.
In fact, Jacob, we are
yes.
getting, we are almost run out of time. Maybe like if you can summarize it up in a few minutes, that would be.
All right, no problem, no problem. So
actually,
basically, we leverage a context, an approach called stochastic computing, where we convert a complex of, we saw that computing the expected, the value function comprises computing expectations that has like a summation of product terms. So implementing on hardware products is very, very costly and requires full adders, and therefore we are able to replace computing expectations using averaging or summation over terms that are generated using a certain probabilistic distribution, and so this leads to a much higher energy efficiency because we are replacing multiplication with simple averaging. This is a approach that has been introduced in the many years ago by Johnny Foy Norman, and so that leads to further gains in terms of power and delay efficiencies. And here we showed how stochastic computing works in our context compared to, again, Q-learning, where we use a different number of samples to do this averaging when computing the expected value function. And we have also compared to deep Q-learning in our context, where we can see that even in compared to deep Q-learning, we observe a much faster convergence and lower average cost. Now, the last thing that I want to quickly cover about is about AR streaming, where we have like a big project where we are trying to design the the hybrid meeting room or conference room of the future, where some people will be physically present and some people will be virtual present, and being teleported there using augmented reality. And this is a high-level illustration of the system where we have physical participants wearing AR headsets, and they will be able to see avatars of the people connecting remotely as being physically present in the room. There are like many things that we solve in this big project that is, involving 2 other academic partners. One of the key things that we want to resolve here, and we have made early progress, is how to bring these remote participants to the physical meeting room where the physical participants reside. And in order to do that, we need to construct avatars of the actual person, and this is typically done through the use of dynamic point clouds, which is also known as volumetric videos. And so in order to deliver them to the location where the physical participants are and render them on the AR headsets, we need to deliver in at least 30 of these point clouds within 1 second. However, these point clouds are very enormous data sets, and compressing them still cannot meet the online latency limits that are required. So our approach here is to basically downsample this point cloud. And to those who may not be familiar, this is not like a traditional image or video that you see. If you zoom in, I will show an illustration. This is a new type of data structure where we have like a collection of points with XYZ coordinates, as well as color and transparency attributes. And this data structure can be seen from different directions at the same time. It can be seen also from different distances, and it serves the basis for augmented reality telepresence. So our approach is to stream basically downsample the point cloud quite a lot to be able to stream it in real time, and then upsample it, super resolve it at the client. So we are the first, we have proposed the first study that in this context explores a deep learning model for point cloud color upsampling, where at the sender, we will basically send low resolution geometry and color coordinate information. And then in the receiver, the the geometry transformation will be upsampled using existing approaches. There has been much more progress on geometry upsampling. And then, based on the low resolution coordinates and colors and the high resolution coordinates, we'll carry out upsampling of the color values using our approach. Now, our approach, the structure of our, neural network-based approach is shown here. In the interest of time, I will save you the details. But basically, we're leveraging deep learning and sparse convolution, which has linear complexity to extract features, the learning features, and then to do color prediction for the high resolution geometry cloud. We use a multi-layer perceptron. We demonstrate runtime memory storage gains where we're able to colorize 1 million points at 30 milliseconds using a 3 megabyte learning model, and the complexity is linear. We can also do our arbitrary ratio upsampling, meaning from 1x to 10x, without the need to retrain or have multiple models, and we have observed or demonstrate significant gains on a state-of-the-art solution. And here is a table that illustrates, the performance of our approach on a data set that comprises only, faces of people, and also a data set that comprises, the full body of a person. And we can see that compared to these other approaches that are mostly neural network based, we provide a better PSNR value, visual quality. This is basically parameterized with a different model size, and as the model size improves, we slightly improve in quality as well. And we can see that for the model of size of 3 megabytes per second, 3 megabytes, we meet latency of around 29 milliseconds per point cloud. So that means for 30 instances of this point cloud, we'll be around 1 second. And, the paper is online, we have submitted to CVPR, and you're welcome to take a look. And lastly, I would like to talk briefly about a project that we have on interdisciplinary application of some of the technology we explore, where we are basically developing technology that will help train people with low vision disability learn some tasks that we take for granted, such as how to safely cross a street. And within this context, we have designed room size VR simulator, and we have also headset alternative of it, where a person will be basically monitored using different sensors and will be trained how to decide when is the safest time for the person to start crossing the street, because these people cannot their vision is impaired, so they cannot make decisions solely based on their vision. And so our system at the high level comprises a virtual reality environment that is controlled by an AI-based agent that controls the training and gives instruction to the user and monitors the performance of the user. And our goal is to avoid the need for the person to train with an actual person in a real street settings. And we have been able to show that that the improvement in terms of safety is same whether you train with a person or you train with our system. And the graph here shows the improvement in a safety score, a metric that is typically used. Now, to explain what is low vision, so this is an impairment of the vision of a person that severely impacts the ability of this person to carry out many activities of daily living, and it has a negative effect on the physical and mental health. It cannot be corrected, unfortunately, using eyeglasses, lenses, and surgery, because the vision impairment is more significant than that. And it affects several percent of the population in the US. So the way to deal with this is to address this challenge through orientation mobility training, and this is called visual rehabilitation. But this involves a trainer, a certified specialist, and there are not so many of them in the US. They're very costly. This is not covered by health insurance, and people who have these disabilities, they typically are low income or unemployed and live remotely from the areas where these specialists are present. And so our approach comprises 3 key novelties. One is a virtual reality environment, which is a safe, content-rich environment for learning the orientation mobility skills. It has an AI-based agent that doesn't involve human intervention or human involvement to carry out the training and the evaluation before this is actually tested in a real street. And then, the whole, solution can be deployed over the internet. So that means this can be carried out in a location that is very convenient for a trainee. You don't need to go to a major hospital that may be far away from where you live. And so with that, I would like to thank for your attention. And I'm sorry, I probably went a little over time, and I would like to leave the floor open for questions and remind again that we have graduate research openings at the broad intersection of the areas listed here. And we carry out a lot of interdisciplinary work, if you may be interested as well. And finally, if you pursue some of the areas that I discussed, we also have data sets to share that can be maybe helpful for your investigations. So with that, I thank you again, and I leave the floor open for questions and give it over to Zafer again.
Thank you very much, Jacob, for this very nice and interesting presentation. Well, actually, there are really interesting developments, apparently. So maybe, yeah, among the audience, I will first ask if there's any questions to our speaker.
And you can also type your question in the chat box. I think, like, we can also do that, right, Zafer? So
yeah, sure, definitely. Chat option is also available. Maybe in the meantime, actually, I was interested quite a lot in the first part, second part, and third part, so that will be too long. But I just like to ask you, well, kind of metrics that you used in the beginning was only distortion based.
yes.
But in the fields, there are people trying to figure out like perception versus distortion trade-off, how it can be transferred. Potentially, it depends on the underlying application, like if it is for medicine, like telemedicine type of things. So, for example, your viewport quality metric, I guess, was on PSNR on Y channel. But how does this translate into also perception? Is there any, let's say,
Thank you.
right? Yeah.
Thank you, Zafer. That is a very good question, and it has been asked before. So there is like a strong correlation between like a PSNR, and as you mentioned, this is measured on the luminance component of the signal, and the luminance component typically captures the magnitude or the intensity of the video signal, where the two color components CR and CB capture only the color information. And there is a strong correlation, studies have shown, between like a PSNR and other metrics. In fact, as I was scrolling through my slides, we also have some results where we show like also measurements of visual quality using SSIM, which is another metric that you may be familiar with. And one facility of using PSNR also is it allows us to formulate analytical models and basically capture the overall system performance as a function of some critical system parameter, like how much data it is assigned, or how much computational capabilities are assigned. Whereas if we try to use some like a metric that may be subjective and that may involve evaluation, with people, it may be hard to have some analysis attached to it. So one of the reasons that we use this is, again, the ability to basically relate on a very high level concepts such as distortion, rate, computation, keeping in mind that, people have shown that PSNR also correlates well with other types of metrics. But I would be also excited to discuss with you further offline, the ability to also integrate metrics that may be fitting for the specific type of immersive application, where some other things may count more than just the visual quality. That's a good point that you have.
No, in terms of latency in the algorithmic side and in the communication side, maybe time to time perception quality might also just matters depending on the application. But yeah, thanks a lot. Any questions to our speaker again? Well, not many, but well, actually, I like to chat with you later on about the PSD, the post-decision state learning thing. That sounds really interesting and cool.
Okay.
We can do that offline, maybe.
Yes.
Thank you very much, Jacob. Once again, this was a lot of results with a lot of enthusiasm in it. So, and for those who will watch it later on, you can always reach out to Jacob via email, I suppose, the best way.
Yes.
For the open positions as well. Thanks
Yes,
again.
definitely. And, like we can discuss offline, as we said, like I listed some of the papers here, like, and they're all online for the post-decision state. We have published a few journal papers that describe this. And the tutorial paper has like a very nice summary of all these advances. We are using it, in fact, we are integrating it, in fact, now with deep learning for training of robots, like to carry out, because typically like in robot training, people use Q-learning, to train a robot to learn a task. And that requires a lot of trials, and roboticists are interested to accelerate the learning. And so we are applying this to robot locomotion. It has like a variety of applications, in fact.
Is there a direct connection, by the way, with the buffer replay approach?
Yes. So we have integrated, yes. Buffer replay is, like, in fact, like in the tutorial paper that I mentioned in the Communications magazine, we discuss, how this could be used to basically, like, implement buffer replay without like generating a lot of samples. So buffer replay is basically like you store a number of samples of previous data, okay? And then, like you go back and use those samples to improve your deep learning strategy. Now, our virtual experience can save you from generating those samples to begin with, because it gives you a way to know what is this value function for samples that you don't need to generate, meaning for state values that you don't need to go to.
That sounds great. Yeah,
provides a way to like bypass like buffer replay, where again that is used in training of deep learning models. So that like you have some prior samples, and then you go back to your buffer, and the reason why it's called replay, you store some samples from your model from the past, and then you go back to it and you randomly sample it, and then you use this to improve your model as you're adapting your model over new data.
Yeah, well, if there are no more questions, we can thank our speaker again. Thank you, Jacob. It was great to see you once again. And let's keep in touch.
Thank you, everyone. Bye. Take care. Thank you for having me.